Welcome back to the Deep Dive. Today, we are putting our stopwatch on one of the most fundamental areas of chemistry, reaction kinetics.
That's right.
We're tackling the question of speed, how fast or, how slow reactions happen, and maybe more importantly, why we can change that speed.
Exactly. Our mission today is to really distill the core concepts. We'll get into the definitions, the lab calculations, and the two big theories that really govern everything, collision theory and the Boltzmann distribution.
Okay, let's start with the absolute basics, section 9.1, defining rate. So reaction kinetics. It's just the study of reaction speed, right?
It is, and the rate of reaction itself has a very specific definition. It's the change in concentration of a substance per unit of time.
A substance meaning either a reactant disappearing or a product appearing.
Precisely. And since concentration is in moles per cubic decimeter, and time is usually seconds, our standard unit becomes moldy AO.
That makes perfect sense. So if we're in the lab, how do we actually follow a reaction? The sources mention two main approaches, sampling and continuous methods.
Yeah, and sampling is, well, it's the more hands-on way to do it. You have to physically stop the reaction at different points in time.
Oh.
You take a tiny bit of the mixture out, and then you have to, and this is a key term, you have to quench it.
Quench. Right. That's just stopping the reaction cold, isn't it?
Exactly. You have to freeze that moment in time, maybe by dunking it in ice water or adding something that kills a reactant. Once it's quenched, you can analyze it, say with the titration, to see how much of a reactant is left.
Okay, that sounds pretty reliable, but you're destroying the sample each time.
Yeah.
The continuous methods sound a bit more, I don't know, elegant. You're just watching.
They are, and they're much more efficient. You really need to know 4 of these. First up is colorimetry.
For reactions with a color change.
Yep. If something's fading or getting darker, like iodine in a reaction, you can just measure how much light it's absorbing over time. Simple.
And the second one.
Conductivity meters. If your reaction is making ions or using them up, the electrical conductivity of the solution will change. You can just stick a probe in and watch the numbers change.
So like in the hydrolysis of a bromoalkane, where you're going from neutral molecules to charged ions.
Exactly. And there's a really neat detail here. The type of ion matters. Little tiny ions like He or OHACE, they zip around in solution and conduct electricity incredibly well.
Ah, so even if you're just swapping one ion for another, if you make a smaller, more mobile one, you'll see a big jump in conductivity.
You've got it. That's a great point for you to remember.
Okay, so that's 2. What about reactions that produce a gas?
Well, that's the third and maybe the most straightforward method. You just measure the change in gas volume or pressure. Think of calcium carbonate and acid.
You just collect the KO in a gas syringe and time it.
Exactly. And last, for really subtle changes, there's the dilatometer.
Right, this one blew my mind. It measures tiny changes in the liquid's volume, but it needs temperature control to plus or minus 0.001 degrees Celsius. Why so precise?
That is a fantastic question. It gets right to the heart of kinetics. Because liquids expand and contract with temperature, right?
Of course.
Well, the tiny volume change from the reaction itself would be completely swamped by any tiny fluctuation in room temperature. And since rate is so incredibly sensitive to temperature, you have to lock it down. You have to be sure you're only measuring the chemical change.
That really drives home how important temperature is. Okay, let's move to the graphs. When you plot concentration versus time, you get a curve. It starts steep, then it levels off. Why?
It's pretty intuitive, really. The reactants are getting used up. At the start, the concentration is at its maximum, so collisions are happening all the time. The reaction is fast. That's your steep slope.
And as it goes on, there's less stuff to react, so collisions are less frequent, and the reaction just slows down. The curve flattens out.
Exactly. Which is why a simple average rate over the whole reaction is, well, it's pretty useless. You need the rate at a specific moment, the instantaneous rate.
And to get that, you can't just look at the curve. You have to draw a tangent.
You do. You find the exact point on the curve you're interested in, and then you draw a straight line that just kisses the curve at that one single point.
And then it's just basic math, right?
Yeah.
The gradient of that tangent line, the change in y over the change in x, gives you the rate.
Precisely. So in the cyclopropane example from the source, they find the point at 10 minutes. They draw the tangent, they calculate the gradient.
And they get a negative number because the reactant is decreasing. But we always state the rate itself as a positive value.
Yes. And after converting minutes to seconds, you get your answer in the right units. But the really profound thing they found was that if you plot the rate you just calculated against the concentration at that moment,
You get a straight line.
you get a straight line. The rate is directly proportional to how much stuff you have. A foundational discovery.
Okay, so we've covered the what and how. Let's get to the why. Collision theory.
Right. This is the bedrock. It says for a reaction to happen, particles have to collide. But, and this is a big but, that's not enough.
Just bumping into each other isn't a reaction.
Not at all. Two things have to be true for that collision to be what we call effective. First, they have to hit each other with the right geometric orientation. And second, they have to collide with sufficient energy.
If they don't have enough energy, they just bounce off each other. An ineffective collision. What is sufficient energy?
That's the activation energy, E with a subscript A. It's the absolute minimum amount of energy needed to make the collision work. Think of it like a toll you have to pay to get through the barrier.
And we can see this barrier on those reaction pathway diagrams, right? The plots of energy versus the progress of the reaction.
Yes, the activation energy is always that hump. It's the energy you have to put in to get from the reactants up to the peak of the curve, the transition state.
And that hump is there, whether the reaction is exothermic or endothermic. That's always an uphill climb to start.
Always. So collision theory gives us two clear ways to speed up a reaction.
Okay.
You either make collisions happen more often, or you increase the percentage of collisions that have enough energy to beat the barrier.
And that perfectly sets up our next two sections. The effective concentration and pressure versus the effective temperature.
It really does.
So section 9.2, concentration and pressure. If we increase the concentration of something in a solution, we're just crowding more particles into the same space.
You're packing them in, which means they have less room to move before they bump into something else. The result is just more frequent collisions.
And there's that key word again, frequency. It's not just more collisions, it's more collisions per second.
Absolutely crucial distinction. You have to mention the time component. Doubling the concentration doubles the collision frequency. It's a direct relationship. Same goes for pressure and gases.
Right. Now for the really interesting one, section 9.3, temperature. This needs a whole new diagram, the Boltzmann distribution curve.
Yes, it does. Because temperature is a bit more complex. This curve shows you the spread of kinetic energies across all the molecules in your sample.
It's not a neat bell curve, is it? It's lopsided. Most molecules are somewhere in the middle, energy-wise, but a few are really slow and a few are super, super energetic.
That's the shape. And on that energy axis, we can mark our activation energy, our EA. And you can see at a normal temperature, only a tiny fraction of molecules, the area under the far right tail of the curve, actually have enough energy to react.
So what happens when we heat things up?
Two things happen. One is minor, one is major. The minor effect is that, yes, the particles all move a bit faster, so collision frequency goes up slightly.
But that's not the main story.
Not at all. The major effect is what happens to the shape of the curve. As you increase the temperature, the whole curve flattens out and spreads to the right.
Okay, so the average energy is higher.
It is, but what's critical is that the area under the curve, beyond the activation energy line, it gets much, much bigger.
Ah, I see. So the EA barrier itself hasn't moved, but a much larger proportion of the molecules now have enough energy to get over it.
That's it. And the effect is huge. It's exponential. A small 10-degree rise in temperature can often double the reaction rate simply because it might double the number of molecules that possess that critical activation energy.
It's not about speed, it's about the proportion of successful collisions.
Fantastic. That brings us to our last factor, section 9.4, catalysis.
The clever shortcut. A catalyst is a substance that speeds up a reaction, but, doesn't get used up itself.
So how does it work? It doesn't add energy like temperature does?
No. It does something much smarter. It provides an entirely different reaction pathway, a new mechanism that has a lower activation energy.
So it lowers the barrier. If we look back at our Boltzmann curve, the curve of molecular energy stays exactly the same because we haven't changed the temperature.
Correct. The molecules are just as they were, but the EA line, the goalpost, we've now shifted it way to the left.
So suddenly, a massive chunk of the molecules that were previously too slow, that couldn't react, now have enough energy.
Precisely. The catalyst just redefines what it takes to be successful. And we have two main types of these, right? Homogeneous and heterogeneous?
We do. Homogeneous is when the catalyst is in the same phase as the reactants. Everything's dissolved in the same solution, for example.
Then heterogeneous.
That's when they're in different phases. This is huge in industry. You might have gases reacting on the surface of a solid catalyst, like iron in the Haber process. The solid surface is where the magic happens. It grabs the molecules, weakens their bonds, and provides that low-energy shortcut.
This has been a fantastic tour of reaction kinetics. Let's do a quick-fire summary of the absolute key takeaways.
Go for it.
Okay. 1. Rate is change in concentration over time. We find the instantaneous rate by drawing a tangent on a graph.
2. Collision theory. For a reaction, you need collisions with enough energy, the activation energy, and the correct orientation.
3. Concentration and pressure. They increase rate by increasing the frequency of collisions.
4. Temperature. It mainly increases rate by increasing the proportion of molecules that have energy greater than the activation energy. That's the Boltzmann curve.
And finally, catalysts. They don't give molecules more energy. They provide a new path with a lower activation energy.
Perfect.
Okay, so here's a final thought for you to take away. We know that high temperature can speed up reactions, but it can also be destructive. It can denature an enzyme or decompose a sensitive product.
Right.
So imagine you're an industrial chemist. You have a reaction that needs a high-temperature catalyst to go at a decent speed, but your valuable product breaks down at that high temperature. Using the principles of heterogeneous catalysis, where the reaction happens on a surface, how could you design a process to get that fast rate while also protecting your final product from getting destroyed?
That's a great puzzle. It forces you to think about how the reaction environment, right there on the catalyst surface might be different from the overall conditions in the reactor. How could you get the product away from the heat fast?
Something to chew on. It really connects the theory to real-world problem solving.
A great place to leave it. Thank you for joining us for this deep dive into what makes reactions tick.
We'll catch you next time for more essential knowledge.